All right, everyone, June 11th. All right, today's goal is segment tree. We know how to do this, right? We already know. It's not difficult. It's just, we don't know if this method will work, but most likely it will. But we have to implement segment tree for every single row and every single column. This is ridiculous, but we have to do it. And I need to figure out a easy way to implement segment tree. But it's never easy when you do segment tree. Never. And I was trying to think whether we can cheat by using binary index tree. But we cannot cheat with binary index tree for minimum. But anyway, today's challenge is very easy. Summary ranges. You're given a sort of unique array, okay? A range is a set of all integers from A to B inclusive. Return the smallest sorted list of ranges that cover all the numbers in the array exactly. That is, each element of nums is covered by exactly one of the ranges. And there is no integer such that it is in one of the range, but not in nums. I see. Hey, this is really easy. All right. It is, because we just need to do one trip down and it should be good enough. All right, we have 0, 1, 2, 4, 5, 7. We start from 0. If it's consecutive, keep going. Not consecutive, we do a range, boom, and then we start again. Consecutive, not consecutive, boom. Last one, take, right? So all we need to do is to record the first one and okay, let's code it. So this is more like a programming problem. It's all about programming. How do we make sure we handle all the situations? We have a result. Then what? We have a pre. So we need to know the start. I say start is nums 0, but nums length can be 0. What if nums length is 0? Then I think we shall return. That's a good question. I don't know. Shall we return this if we don't have anything like this? Or yes. Okay, now we say if not nums, so I return this. This is the start, right? And then we say for I range 1 to line nums. Okay, if nums I minus nums I minus 1 is larger than 1, and they're all unique, right? So if it's larger than 1, since it's not consecutive, jeez, man. If it's not consecutive, we need to add something to the result. Now, how do we add? We have the start, we just need to end. And we know the end. The end is nums I minus 1. So what we need to do is to see if st is equal to nums I minus 1. That means it's a single value, right? That means it's a single value. And then rest shall append str st, done. Else, that means it's not a single value, so we have a range. And it's inclusive, so we say dot append str st plus, now let's do f string. More fun, S string. So I will start, do this, and nums I minus 1, right? So once we do all that, we have to reset the starting position. The starting position shall be nums I. Okay, and then that's it. If it's equal to, then we don't do anything. We just keep going, keep going, keep going. And once we're done, right, we have to consider the last one, right? The last one. And we have to check. It's basically do this one more time, but for the last value. So I shall do the last one. So if it's equal to -1, we do this. Otherwise, we need to do this. Okay, once we're done, we'll return res. Okay, let's give this a shot. Looks about right. Let's do a couple more. Let's say, yeah, why don't we do minus, right? There should be this. Okay. Okay. Then how about a 1, 3, 5, 7, 9, 11. Okay, last check. Actually, one more check. Individual. Yeah, I think we're good. All right, try it. Nice. Good. This is the third time we've done this. This is the last time. Yeah, that's the same. Okie dokie. To do 8. Nothing to say. Let's just. What's the solution? Fix left bound. Use a while loop so you don't have to do it twice. Yeah, I don't like while loop. Anyway, that's done. Okay, that's done. All right, back here. All right, let's do this. Let's do this. Again, I think we have to go back to yesterday's. Yeah, so basically this is what we want, right? We're gonna start from this position. We just go like row by row, row by row. And for each position, we need to find the minimum in the range for the row and the minimum in the range in the column. And when we do that, the value can be the minimum plus 1. That's it. So we just need to we need to implement segment tree. Do the segment tree for this. We can do this. We can do this. Segment tree. We implement segment tree a couple of times. Still definitely a weakness on my side, but not afraid. Okay, so what do we need to initiate with for segment tree? With segment tree, we need to initiate with the largest, right? The largest index, which we can just set by n, okay, the size. Okay, and we just say self dot, I can say n equal to n. Okay, there's a total range, right? Total range. And then we'll start from 0 to n, and we need a tree itself. So self dot root is gonna be 0. I don't know if we need this, but we also need self dot tree, and we will use a dictionary for this. Yes, we'll use a dictionary for this. So we just say it's going to be a dictionary. So two methods. One is update. Okay, update is we want to update a value. Actually, we should put it as a minimum, right? Segment tree. We want to put a value at position, right? At a position. That's what it is. Okay, and we also need a query. Query is we want to find a min value from query start to query end. This shall give me a min value. Now to implement update, we need to do a inner function, right? A private function for update. And this one tells me I want to update something in a value, update a position in a range. So I need to do this is a range. What is this range? This range is range left, query start, range start. Okay, range start, range end. We want to update a value in it at a position at a pos. And this one will return none. Okay, so have range start, range end. Oh, one more thing. We also need a index. Okay, index is the tree index, right? Do we need a tree index? We do need a tree index. And the tree index can start from 0. Then what? We'll find the middle, right? We'll find the middle. And if value is going to be on one side, right, then we do update this side. And, okay, so when do we assign the value? We say if range start equal to range end and equal to value, when that happens, no, equal to position, when that happens, self.tree rs, right? No, index. Its index is value update. We update it to be position, okay? Else, then we say mid equal to rs plus re divided by 2. Okay, that's the middle, and we'll put middle on the left hand side. So if that position is smaller or equal to the middle, then we'll call update again to the left subtree. And the left subtree is 2 times index plus 1, range left, a start, mid, and value and position. Doesn't change. These do not change. Okay, and else the position is larger than middle, so we need to go for the right hand side. So self dot update 2 times index plus 2. We start from mid plus 1 to the end, value and the position. So we'll do all that, right? Once we finish all that update, then my current value needs to be changed because I want the min, right? So I shall say self.tree index shall equal to the minimum of self.tree my right child and my right child. Done. That is update. So here we can just call self.update. Well, we start from 0 because that's the root, and we need the left range start. They always start with 0. Range, that's always start from .n minus 1. Value is value, and the position is position. So we call this, done, right? And now query. So for query, same deal. We need to do a private query, which basically says we have because we want to query this range, right? Giving me the range. And what I need to do is giving me this entire range. I want to query this smaller range. So we have range start, range end, query start, query end. And of course, we need an index as well, right? And this one will return an integer. Okay, so we have the query start and query end, right? Now what do we do? Well, here is, let me think. So we have a query, we have the current range, and then we have a query, right? So the query, if the query is larger than the current range, then it should just return whatever the current range is. Okay? If the query is smaller than the range, then it depending on the middle, right? That makes sense, right? So we say if query start is smaller or equal to range start and query end is larger or equal to range end. So the query range is bigger than the given range. Then we shall just return whatever self.tree index. Okay. Otherwise, then we'll do a mid equal to range start range end divided by 2. Okay. Then what we need to do is, there's another possibility, the impossible possibility. If query start is larger than range end, okay, or query end is smaller than range start, then we return math.infinity. Right? That's math.infinity. So now everybody is mingled together, so we have a mid. Okay? Then we say if query end is smaller or equal to mid, then we'll return self.query. Right, so query end is on the left hand side of the mid, so we only go to the left subtree. So it's 2 times index plus 1. Range start, mid, query start, query end. Okay? If query start is larger than mid, okay, then we go to the right subtree. So we'll query it 2 times index plus 2, right? And mid plus 1, range end, query start, query end. Else, so query end is larger than mid and query start is smaller or equal to mid. So when that happens, we need to return the minimum of 2 queries, right? So we'll do 1 query here and we'll do another query here, but we also need to change the range a little bit. So this is fine, but this is not the query end because we already do, so this will be mid, right? And this is not going to be query start, this is going to be mid plus 1. Okay, so now actual query. So we should just return, right? Return self.query root range start, range end, query start, and a query end. Which means this is not necessary. What do you think? I have no clue if this works. Dear God. So we need rows, right? And we need columns. So we shall say sec tree, row sec tree. How about that? Row sec trees. We need mn. Len grid. Oh, are they the same? No, they're not the same. Len grid 0. Do we have a 0 instance? We don't have a 0 instance. So row sec tree shall equal to, for each row, right? For each row. For each row. So for this in range M, okay? For this in range M, for each row we're gonna do a min sec tree and the size. The size is n, right? And the column sec trees shall equal to min sec tree m for this in range n. Okay, so each row and each column have their sec trees. Now we're gonna start from this position, okay? This position. In this position, the value is 1, which means we shall do row sec tree m minus 1. That's the last row. So in this sec tree dot update, right? This sec tree dot update a value. What value? Well, we'll update a value is gonna be 1, and its position is gonna be n minus 1, right? That's that. And a column sec tree, the last column dot update, right, is also 1, and the value is m minus 1, right? Because that's its position. So with that in mind, now we can say for I in range, I is row, so m minus 1, right? Because we're in the last row, minus 1. For j in range, now that's not n minus 1, that should be n minus 2, because we start from this position, right? We start from here. That's n minus 1, that's n minus 2, minus 1. Okay, so now we're looking at this position. What do we do, right? What do? We go, of course, we cannot go down, right? Why can we not go down? Because we just cannot go down. And in fact, this actually shall be n minus 1. We just need to put another condition, which is cannot go that way, right? Can we, when we query, let's see, if we here, when we query, we shall query something. That's actually interesting. That's actually very interesting. If I want to query this, right, it's going to be this plus 1, which will be m. So we're going from m to m minus 1, which is wrong, right? This is m minus 1. Then m, well, larger than range end, because range end is this. So we actually don't need to. This will return math.inf, right? So okay, what we need to do is to find the current. So the current shall equal to row sec tree I, right, dot query something, and column sec tree dot query something, right? And once we query these, it's just a minimum. When we query that, we need to find the minimum of these two, and then plus 1. So what do we query? We shall query, enjoy. This should be j, right? We shall query this thing, right? How much we can go, depending on how much this one is, right? How much this one is. Because like there's 3, we can go 1, 2, 3. So whatever, so we do row first, okay, row. So whatever the value, the grid value, First things first. If grid ij is equal to 0, okay? So we basically cannot query anything. Yes, it's fine. Will this also work with this implementation? Because we'll say we start from this position and then we'll end at this position, right? So we can actually do this. So if this or query start is larger than query end, right? When that happens, then yeah, it's gonna be impossible. So we don't have to check. That's the thing. We don't have to check. We do not have to check. So now what is this query? We want a query start. But the query start will definitely be for a row is j plus 1, right? Whatever you are, j plus 1. Query end, okay? Query end. So what is your query end? Your query end is going to be whatever your j, then plus grid ij, right? You start from here, query end is whatever this is j plus 1, 2, 3. That's your query end. Okay, so that is for the row. And for the column is going to be I plus 1, I plus grid ij. So this, whatever value it comes out, plus 1 is going to be the current. And we need to do row sectree dot update. Okay, update what? Update the value, which is the current at the position. What is the current position for the row? All right, the current position for the row is your j. We'll update the position at j. And the column secretary is going to be j dot update your current value of I. Right? So we do that. We finish this. Then we check this. And we check this. Right? When we're done, we go check this and this and this and this. And all the way we checked the first one. Right? So we go through everything. Now what we need to do is to find this value. How do we find this value? Exactly. How do we find this value? Well, we have the current. And the last one is going to be I0j. So we just return current. Oh, if this one will pass, that will be quite, I'll be quite happy. Quite happy. So let's see. Normally, these things don't do in first attempt. Yeah, I forgot the -1, so I have to do -1. Don't worry, we'll do -1. So return current if current is smaller than math.inf, else -1. Okay, we have grid. This one is minimum something grid. Key error 5. That is interesting. That is interesting. Key error. We have a key error. Dude. Oh, update. Why do we have a key error? So we call update. Okay, then we have this and this. So shall be .get. Okay. Math.inf. And this is .get. So yeah, because we haven't traversed there yet, right? If we have not traversed there yet, then we just put math.inf. Not correct. Not correct. That's cool. That's cool. That's cool. That's cool. Let's do this. That is totally cool. I just want to record. I want to see what the hell do we get for every single position. ij equals current. Okay, then we say for row in dp, print row. That is bonkers. This is not right. Because this should be 1. But I'm doing this way. Holy crap. Maybe I should, if I is equal to n minus 1 and j equal to n minus 1. Continue. Still not right. That's fine. That's fine. So we are running this one already. Okay. So first one, we escape the first one, right? The next one, j is n minus 2, so j is going to be here. Oh, hold a second. This is correct. Inf. This. What's this position? How come this is 3? How come this is 3? Right? This is 3. This is not right. What if I minimum this thing? Just throwing ideas at it. Nope. Did this query thing wrong? That's the thing. I don't know if it's correct. I think it's correct, but hold on. Let's see. Print ij. I just want to see the row for now. I3 0 1 2 3 J2 I3 J0 1 2 0 1, this one. How is this 2? I only have 1 in this. What did I get wrong? Exactly. How is it the minimum in this? I said this is 1, right? Let's print row I dot tree. I want to see. What? Value. There we go. Yep, I knew it. I knew it. That's it. That's it. It's a typo. It's like, where does those value came from, right? That doesn't make any sense. Of course, it doesn't make any sense because it's supposed to be value. I put position in there. Boom. All right, let's hope. Let's hope it's enough. Come on. Oh, I'm gonna strangle myself. Seriously, strangle myself. What is this? A 0. By itself. By itself. Shouldn't this be -1? No. There should be 1. Right? Because you can reach it. But anyway, so we'll do this. Current equals to the continue. You shouldn't do current. Can I do let's say res equal to row secretary 0 dot query. We're gonna query 0 to 0. Yeah, we'll query this position, right? This is Yep. Try this. Does this one work? Okay. Let's go for it. Huh. Come on. Come on. Lordy. Timeout. Damn. I already did the difficult part, but it still times out. Whoo-wee. Is it the implementation of the segment tree is not good enough? To me, it looks pretty standard. I guess seriously, it's looks very standard. So what the hell is this thing? Dear Lord. Wait, hold on, hold a second. Let's view all. I think this is a giant column, right? It's like a giant column. Ah, I see. No, I only need one because it's a giant column. So there's no rows. But I create that many row segment trees. Huh. Okay. Okay, so we have to be a little bit smarter, right? We have to be a little bit smarter. Yeah, this is, so if we have even out, I think we're good. It's only when we have very short, like very fat grid or very thin grid, that's when the problem happens. So what do we do if we have a very thin one or a very fat one? Is there any special trick we can do? Let's just say we have just one column, okay? This is 0, right? Then everything we only need to consider this. We don't have to consider this. We just need to know the smallest value in this range, right? Smallest value in this range. Doesn't really matter whatever range it is. We just need to know the smallest value in the range. Row-wise, there's no row because each row is going to be, but it's also going to be fast because you query this immediately just return. But I think it's the just the setup. Because you have so many rows, you have so many of this to set up. I don't know. What do you say? Yeah, I don't know. Or okay, I just want to know. Yeah, I'm not playing with this thing. I want to know which part is actually the bottleneck. Okay, which part is the bottleneck? Yeah, we know it's very slow. That's okay. Let's say we don't do this. Okay. There's no row. And I want to change this. Should I just don't do row? I mean, we can just do math.inf. Don't do row. We do column. Want to be faster? Nope. Nope, that is not. That is not the bottleneck. The bottleneck is still the implementation. Not really implementation. But if you think about it, everybody is the same value, right? Everybody is the same value. Which just means from this to a certain position, this to a certain position, this to a certain position. Do we not do the segment tree right? Oh my god. Wait, do I not have a segment tree? No. 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 Oh, you're kidding me, man. I have to use lazy? Alright, what do we do? What do we do? Seemed to me maybe we shall lazy it. Then we have to try to understand lazy again. Oh, God. God, man. I do not have the mental capacity today to do this. Okay, so in summary, this one works. Okay. However much this one works. Okay, so it works, but TLE. All right, my guess is that we have to use a better implementation of segment tree. For example, a lazy seg tree. So this is what we're gonna do. Let's do it tomorrow. All right, let's do it tomorrow. God. I have a template, but I have to understand this thing first. Like, I already don't remember why I need this. Why did I need this in the first place? I don't know. I put it there. I don't understand. I think this is just initialization, right? It's initialize the segment tree. I said it might not be necessary. Yeah, however you want to initialize, it doesn't really matter. Anyway, update. I'll have a lazy, do this. Do this. Wait. That. Hold a second. Hold a second. My update. I think the update is... Just ignore the lazy part. Segment start. What's this U? Update start. Segment start is larger than segment end. Update start larger than update start is larger than segment end. Or update end. Yeah, that's all the... Yeah, we didn't do this. We did not do this. Let's put it here. Of course, I don't call it segment start. I call it range start larger than... Oh, that's why. Because update is an entire thing. So all the RS, let's change all the RS to segment start then. Segment start. This is changing to segment end. Okay, segment start, segment end. Oh my god. Completely wrong, man. What the hell? It should be segment end. But there are too many RE. Segment end. Segment end. Segment end. Okay, so segment start, segment end. And a query start we can call, is that we call query start? Yes, don't have to change this. But then I need more value, right? But instead of position, update start, update end. Then we can do this, right? And then what? Right? Segment start larger than update start. Yes, this is true. Otherwise, we'll do mid. Then we'll update. Okay, we'll update both. Right. Segment start, mid. Yeah, we'll have to do update start, update end. Update start, update end. Same thing. Right? Update start, update end. And after that, this. I forgot a self dot for all the oh my god, man. Forgot a self. I forgot all the self. Oh my god. And lazy. Right? That looked more like it. Okay. Now I don't think we changed anything. It's the same. It's the same. I think you do this, it's not gonna make any different. That's just gonna be position and position, right? From position to position. And a query. No, we don't have this yet. This is the impossible case, right? Let's see, impossible case. No. Not US. It's a query S. And a query end. Query S. Query end. Okay. Query S. Query end. Yep. So on the right. Then, if SS is smaller or equal to, query S is smaller or equal to SS, and query end larger than S, and now return. Yep. And then we do this, we do this. Then we just return query and query. So we don't do this. We just do this. Query as query end. Query as query end. Okay. Query as query end. Does it still work? Tree. Where? Self.trees. Yep. But I think it's still not right because I didn't really change anything. Did not change anything. Just make the tree implementation go a little bit better, right? A little bit simpler, but overall it's still the same thing. Yeah, we have to try the lazy one. Yeah, that's not working. Yeah, I'll do it tomorrow. I'll see you guys tomorrow. Adios.